There is an object, small, distant, moving through the inner solar system at 17 kilometers per second. Its light reaches us across 1.4 astronomical units, dim but steady, captured by dozens of instruments scattered across the surface of this world. The photometric data streams in clean stoid. The spectroscopy is textbook. The orbital solution converges beautifully under standard gravitational models. And then, without warning, the brightness shifts. Not gradually, not symmetrically, only when viewed from specific angles. The tail, which should point cleanly away from the sun according to every principle of radiation pressure and solar wind, lags behind by 11 degrees. But only sometimes. Only from certain positions in Earth's orbit. The non-gravitational acceleration vector, usually stable in cometary objects, rotates, not with the object's own spin, with our viewing geometry. One sentence changes the entire framework. The object is not behaving differently. We are simply seeing it from an angle that reveals something we were never supposed to notice. So the question becomes inescapable. Is this an illusion of perspective? Or is the perspective revealing a behavior that only activates when observed from specific coordinates in space? There are objects in the solar system that do not belong here. Not in the sense of mystery or speculation, but in the strict sense of orbital mechanics. They arrive on trajectories that do not close, that do not return, that arc once through the inner system and then escape into the darkness between stars with velocities that nothing born here could ever achieve. On September 13, 2024, the Asteroid Terrestrial Impact Last Alert System, ATLAS, detected one such object at a heliocentric distance of 2.70 inbound, brightening slowly. The designation was mechanical. 3I Atlas, the third confirmed interstellar visitor to pass through our neighborhood since systematic sky surveys began. Follow-up observations came quickly. The Pan-STARRS array in Hawaii confirmed motion. Subaru's wide-field imager captured positional data across 3 consecutive nights. Gaia, in its slow scan of the celestial sphere, registered the object against background stars and logged a proper motion inconsistent with solar-bound orbits. Within 72 hours, the orbital elements were published. Eccentricity 1.031, hyperbolic, unbound. Inclination 78 degrees to the ecliptic plane, steep and retrograde. Perihelion distance projected at 0.910, just inside Earth's orbit, expected passage in late December. Hyperbolic excess velocity 4.2 kilometers per second, modest by interstellar standards, but unmistakable. This was not a long-period comet returning from the Oort cloud. This was something that had spent billions of years in interstellar space, falling toward the sun under gravity alone, with no parent star to anchor it. There had been 2 others before. Ane, Oumuamua, detected in 2017, slender and tumbling, brightening and fading, in ways that resisted easy classification. It left the inner system before most telescopes could be properly tasked. Twy Borisov, discovered in 2019 by an amateur astronomer in Crimea, behaved far more predictably. A classical comet, outgassing carbon monoxide and water, its coma and tail developing cleanly with decreasing solar distance. It was exotic only in origin, not in behavior. 3. Atlas fell somewhere between. Early spectroscopy suggested water ice, simple organics, silicate dust. Nothing alien, nothing strange. But the light curve was irregular. Not chaotic, but structured in ways that did not match rotation alone. And as the object moved deeper into the sun's gravity well, the irregularities did not smooth out. They sharpened. The object brightened faster than predicted. Then, slower. Then faster again. The changes correlated not with distance, but with something else. Something that took weeks to identify. The viewing angle from Earth. The geometry of observation. The position of our instruments relative to the sun, the object, and the plane of its motion. It was as if the object knew where we were looking from. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. Within days, the global network of professional and semi-professional observatories began coordinating observation windows. Gemini North in Hawaii, contributed high-resolution imaging across multiple wavelengths. The Very Large Telescope in Chile dedicated a spectroscopic campaign targeting emission lines from volatiles. JWST, still operational in L2 halo orbit, contributed near-infrared photometry at wavelengths optimized for thermal emission from dust grains. Hubble turned its wide-field camera 3 toward the object during Earth's night-side passes, capturing ultraviolet data that constrained coma chemistry and ion tail structures. ALMA, the Atacama Large Millimeter Array, scanned for carbon monoxide, hydrogen cyanide, and methanol, tracers of cometary composition and activity. Every instrument returned data. Every data set confirmed detection. And every data set showed the same pattern. When 3I Atlas was observed nearly face-on, from a geometry where Earth lay almost directly along the object's trajectory vector, the brightness spiked. The coma appeared denser. The tail structure sharpened. But when the viewing angle shifted, when Earth's orbital motion carried our telescopes to a more oblique line of sight, the brightness dropped. Not uniformly, not symmetrically. Specific wavelengths dimmed faster than others. The ultraviolet emission decayed more rapidly than the optical. The near-infrared remained relatively stable. The millimeter wavelength co-emission did not track with the optical brightness at all. This was not noise. It was not atmospheric distortion or instrumental artifact. CCD stacks from amateur observers in Argentina, South Africa, and Australia confirmed the same phase-dependent brightness changes. Light curves compiled from robotic survey telescopes in New Mexico and Arizona showed the same asymmetry. The data converged. The behavior was real. But what physical process could produce brightness changes that depended so strongly on the observer's position? Cometary jets, the most common explanation for non-uniform brightness, typically rotate with the nucleus, sweeping emission across all viewing angles over time. Dust clouds ejected by sublimation expand spherically, or at least in broad cones aligned with solar heating. Reflected sunlight from an irregular surface changes with rotation phase, but not with the observer's motion through space. Yet 3I Atlas was doing something different. It was responding to geometry, not its own geometry, but ours. Not its orientation in space, but our orientation relative to it. The implications were subtle but deeply strange. Either the object possessed a structure so finely tuned to directional emission that it mimicked intentional beaming, or the emission itself was being shaped by processes that had no analog in standard cometary physics. Under normal conditions, small bodies in the solar system behave predictably. As a comet approaches the sun, solar radiation heats its surface. Water ice, frozen carbon dioxide, methane, and other volatiles begin to sublimate. Gas escapes from the nucleus, carrying microscopic dust grains with it. The gas forms a tenuous atmosphere called a coma, typically spherical in the absence of rotation or strong jets. Sunlight scatters off the dust, making the coma visible. Solar wind, a stream of charged particles flowing outward from the sun, ionizes some of the gas, creating a faint blue ion tail that always points directly away from the sun, regardless of the comet's direction of motion. The dust, less responsive to solar wind but still affected by a radiation pressure, forms a broader curved tail that lags slightly behind the ion tail, following the comet's orbital path. These structures are well understood. Their geometry is predictable. The brightness of a comet typically follows an inverse power law, with heliocentric distance, usually something close to the inverse square of the distance, modified slightly by the activation temperature of dominant ices. For water ice, activity begins around 3O and ramps up steeply inside 2OB. For carbon monoxide, activity can start as far out as 10 Spectroscopy reveals which molecules are present. Photometry reveals how much light is being scattered. Together, these measurements allow researchers to estimate the size, composition, mass loss rate, and rotation state of the nucleus. The models are robust. They have been validated on hundreds of comets. They work. When a new comet is discovered, predictions about its brightness evolution, tail development, and spectroscopic signature are usually accurate to within a factor of 2 or 3, good enough for most purposes. Deviations from predictions are common, but they are usually explainable. A jet pointing toward Earth makes the comet appear brighter. A jet pointing away makes it dimmer. A sudden outburst, caused by a collapse or fracture exposing fresh ice, produces a temporary brightness spike. A slow rotation means jets spend more time pointing in some directions than others, creating periodic brightness variation. But all of these behaviors are tied to the object's own properties: its spin, its surface, its internal structure. They do not depend on where the observer is located. A comet does not change its brightness because Earth has moved. It changes its brightness because it has rotated, or outgassed, or fractured. The behavior is intrinsic, not relational. This is a foundational principle of small body physics. The object behaves according to its own physics. The observer simply records the results. 3I Atlas was violating this principle, and it was doing so consistently. The first anomaly appeared in the non-gravitational acceleration measurements. As gas sublimates from a comet's surface, it carries momentum. This produces a tiny rocket-like thrust that nudges the comet slightly off its purely gravitational trajectory. The effect is small, typically a few millimeters per second squared, but detectable with precise astrometry over weeks or months. For most comets, the direction of this thrust is stable. It points along the axis of maximum outgassing, usually roughly sunward or anti-sunward depending on the comet's rotation and thermal lag. For 3I Atlas, the thrust direction changed. Not gradually, not with a smooth precession that would indicate rotation. It changed when Earth moved. When the angle between Earth, the object, and the Sun shifted by 30 degrees, the measured non-gravitational acceleration vector rotated by 18 degrees. When the angle shifted again, the vector rotated again. The magnitude remained roughly constant, but the direction tracked our motion, not the comet's. Orbital dynamicists ran the data through every model available. They tested asymmetric jet configurations. They simulated tumbling nuclei with multiple active regions. They introduced thermal lag, varying surface compositions, even exotic ices with non-standard sublimation curves. Every model that fit the data required the thrust direction to depend on viewing geometry, a requirement that made no physical sense. The second anomaly was in the tail. Dust tails follow predictable geometries. They curve gently away from the Sun, shaped by radiation pressure and orbital motion. The curvature can be modeled with high precision if the particle size distribution and ejection velocity are known. For 3I Atlas, the tail alignment was wrong. Not by much, 11 degrees, well within measurement precision for a single observation. But the error was systematic. The tail lagged behind where it should be, consistently, across multiple observation epochs. Except when it didn't. When observed from certain angles, the tail alignment corrected. It snapped into the predicted position, within error margins. Then, as Earth continued its orbit, the tail drifted out of alignment again. This was not a measurement artifact. Different instruments, different analysis pipelines, different research groups all reported the same pattern. The tail geometry was conditional. It depended on perspective. And there was a third anomaly, quieter but perhaps more disturbing. The light curve, the record of how the object's brightness changed over time, showed periodic variations consistent with rotation. A nucleus spinning once every 14 hours, tumbling slightly, with 2 or 3 brighter facets that caught sunlight at different angles. Textbook behavior, DART. Except the periodicity was not stable. Over the course of 4 weeks, the rotation period appeared to lengthen by 43 minutes. Then, it shortened again. Not smoothly, but in discrete jumps that coincided with changes in viewing geometry. Rotation periods do not change on weekly timescales. Not for solid bodies. Not without catastrophic fragmentation. Yet 3I Atlas was doing exactly that. The simplest explanation is asymmetric outgassing. If the nucleus has a single dominant jet, and that jet is oriented in a specific direction, then observers along the jet axis will see a brighter, more active object than observers viewing it from the side. This is common. It is expected. But it does not explain why the non-gravitational acceleration vector would rotate with the observer's position. Jets push in the direction they point. They do not push in the direction someone happens to be looking from. A more complex explanation involves rotation. If the nucleus is tumbling chaotically, with multiple jets activating and deactivating as different facets rotate into sunlight, then the net thrust direction and the brightness could both vary in complicated ways. But chaos does not produce correlations. It produces noise. 3. Atlas was not noisy. It was structured. The brightness changes were repeatable. The thrust vector shifts were systematic. This was not chaos. This was pattern. Another possibility is phase-changing materials. Some ices do not sublimate smoothly. They undergo abrupt phase transitions at specific temperatures, triggered by solar heating. If the nucleus contains patches of such material, amorphous water ice crystallizing into cubic or hexagonal forms, or clathrate hydrates releasing trapped gases, then the outgassing rate could change suddenly, producing brightness spikes and non-gravitational kicks that vary with solar distance and illumination angle. But phase changes are triggered by temperature, not by observer position. They depend on where the sun is, not where Earth is. Then there are fractal dust structures. Aggregates of submicron grains, held together by van der Waals forces, can scatter light in highly directional ways, producing brightness enhancements along specific angles. If the dust ejected by 3 Atlas formed such structures, and if those structures aligned preferentially in the anti-sunward direction, then observers positioned along certain sight lines might see anomalously high brightness. This is speculative, but not impossible. It has been proposed for interstellar dust grains. It could apply here, but it still does not explain the non-gravitational acceleration changes. Dust scattering affects what we see, not how the object moves. A more radical explanation involves surface layering. If the nucleus is covered by a thin, optically active crust, perhaps a mantle of refractory organics deposited by previous outgassing events, then the way sunlight interacts with that crust could produce brightness changes that depend on illumination, geometry, viewing angles simultaneously. If the crust is textured at micrometer scales, it could act as a diffraction grating, redirecting light in narrow beams. If those beams happen to sweep across Earth's position as the object rotated, the brightness would spike. This is exotic, but it is physics. It requires no new principles, only unusual conditions. But it strains plausibility. And it still leaves the tail alignment unexplained. At the boundary of conventional explanation lies the possibility of something more unsettling. Not propulsion in the engineered sense, but physics that produces propulsion-like effects without intention. Superfluidity in exotic ices. Quantum coherence in microscopic dust grains. Magnetic fields generated by ionized outflows interacting with the solar wind in ways that produce Lorentz forces on charged particles embedded in the nucleus. These are not proposals. They are edges of the possibility space, regions where known physics becomes difficult to model and observation becomes difficult to interpret. They are mentioned not because they are likely, but because they are less unlikely than what comes next. Because if none of the passive mechanisms work, if asymmetric jets, phase changes, fractal dust, and layered crusts all fail to explain the full set of observations carefully, the hypothesis that the behavior is not incidental, that it is not emerging passively from the object's composition or structure, that it is conditional by design, that 3A Atlas is doing something, not merely being something, and that what it is doing only becomes visible from specific angles, from specific distances, from specific moments in time when the geometry aligns. The object will not remain observable forever. Its trajectory carries it inward now, toward perihelion in late December, where it will pass 0.910 from the Sun, closer than Earth, farther than Venus. Solar heating will intensify. Outgassing will peak. If the object is going to fragment, it will happen then. If hidden volatiles are going to activate, that is when we will see them. After perihelion, 3E, Atlas will begin its outbound journey, accelerating as it climbs out of the Sun's gravity well, fading as the distance grows. By mid-2025, it will be beyond Jupiter's orbit. By 2026, it will be dim enough that only the largest telescopes will be able to track it. By 2027, it will be gone, lost in the noise of deep sky surveys, indistinguishable from distant galaxies and faint stars. There will be no second chance. No follow-up mission. No spacecraft intercept. We get one pass, and then it leaves. So the observations are being coordinated carefully. JWST has been allocated additional observation windows. Hubble will continue ultraviolet monitoring through perihelion. ALMA will track molecular emission as long as the object remains within its observable range. Ground-based photometry campaigns are being organized across 6 continents, synchronized to provide continuous coverage as Earth rotates. Amateur astronomers, with 12-inch and 16-inch telescopes, are being asked to contribute CCD frames, not for discovery, but for light curve density, hundreds of data points per night, enough to catch short-lived outbursts or sudden brightness changes. Theoretical predictions are being refined. If the non-gravitational acceleration continues to rotate with viewing geometry, then specific dates have been identified when the thrust vector should align with or against the object's velocity vector, producing measurable changes in orbital speed. If the tail alignment anomaly is real, then there will be a 10-day window in mid-December when Earth's position should produce maximum misalignment, making the effect easier to measure. If the rotation period is truly variable, then continuous photometry during that same window should reveal whether the changes are smooth or stepwise, periodic or chaotic. None of these predictions are certain. They are conditional. They depend on whether the behavior observed so far continues or whether 3E Atlas is about to do something new. Because that is the other possibility. That what we have seen so far is only the beginning. That the angle-dependent behavior is not the mystery. It is the precursor. That as the object moves deeper into the solar system, as it passes through perihelion, as it reaches some critical distance or temperature or illumination geometry, something else will activate. Something we have not yet seen. Something we are not prepared to interpret. There is a discipline in astronomy that is rarely discussed outside the field. It is the discipline of not knowing, of sitting with uncertainty, of collecting data without forcing interpretation, of allowing an object to remain strange for as long as necessary until the observations accumulate enough weight to collapse the possibility space naturally. This is not the same as ignorance. Ignorance is passive. This is active restraint. It is the deliberate choice to let a question remain open rather than close it prematurely, with an answer that feels satisfying but explains nothing. 3I Atlas is an exercise in this discipline. Every observation adds information. Every new data point constrains the range of viable explanations. But the constraints are tightening slowly, and the shape they are converging toward is not yet clear. It could still be asymmetric outgassing. It could still be exotic dust. It could still be something mundane dressed in unusual geometry. Or it could be something else. Something that does not fit into the categories we have built from centuries of observing objects that were born here, that have orbited the sun for billions of years, that have been shaped by solar wind and radiation pressure and gravitational perturbations into forms we recognize. 3 Atlas was not born here. It spent its formative years, perhaps its entire existence until now, in interstellar space, where temperatures hover 3 degrees above absolute zero, where radiation fields are 1 trillion times weaker, where the nearest gravitational influence is light years away. We do not know what processes operate there. We do not know how ice structures develop in that environment. We do not know whether dust grains grow differently, whether organic chemistry proceeds along different pathways, whether surface textures evolve into configurations that we would never see on a solar system native object. And so we watch. We measure. We model. We compare. We eliminate hypotheses one by one, carefully, without rushing. We sit with the discomfort of not knowing whether the angle-dependent behavior is profound or trivial. We accept that the answer may not arrive before the object leaves. We prepare for the possibility that 3A Atlas will exit the solar system carrying its mystery with it, leaving behind only data and questions, and the faint, lingering suspicion that we were looking at something important, but did not have the tools or the perspective to understand it fully. Because that is the truth of exploration, that most discoveries do not arrive as revelations. They arrive as anomalies, as small deviations from expectation that take years to interpret, as behaviors that seem impossible until they become the foundation for the next generation of models. 3i Atlas is one such anomaly, and whether it resolves into something mundane or something profound, it has already done what every good mystery should do. It has forced us to look more carefully, to question our assumptions, to consider that the universe may still contain behaviors we have not yet imagined, and to remember that sometimes the most important discoveries are the ones that only appear when you look from exactly the right angle.